As you can notice from all those previous contents, in fact, the neural network is a minimizer, is an optimizer that reduces the difference between the predicted value and true value. So that scheme can be can be applied to the regression problem, because in regression problem, the goal of finding a regression model is to find a model that predict as accurately as possible. So it reduces the difference between the predicted value and true value. Okay, so here is a simple example, simple regression example, which is one-dimensional case. There is only one x value and only one y. So let me just copy this part and then paste it into my R session. So this line is just to generate x values from from -6 to 6 with a 0.5 increment. So this one is x value -6, -5.5, -5, and up to 6. Okay. And then to generate y value, what I used is in fact, I used the sigmoid function, 1 over 1 plus exponential minus x. And after that, after this formula, I added an random error, right, from R long function. So what I did is we generate the random number from normal distribution, which means is 0, and the standard deviation is 0.03. And here the length of x is the number of x values that are 25. So by learning this code, in fact, we can generate y values, and because this is only one x and only one y, we can plot those data points in two-dimensional space, and data looks like this one. If you want to add more perturbation here, then you can increase this standard deviation to 0.5. Then there is more error, right? Okay, can you see the difference? Okay, so based on this data set, only one x column and only one y column, and this is a regression problem, we can train a neural network based on this training set. So here, using this nnet function, we specify x, we specify y, and the number of hidden nodes is set to 3, and maximum iteration is set to 100. Then now we have the neural network for regression problem. So this code, what this code does is just to plot the predicted value, because this nn.leg our object contains a predicted value stored at the name of a fitted value. So this one is predicted value, and we plot that predicted value on x space. Then this is the plot of predicted value at each of the x values. Okay, now you can see that it's quite a sigmoid function shaped, right? And then to draw a fitted line, what we do using this command is we make a data frame. We generate more axes where the increment is quite small value, 0.01, from -6 to 6 using this sequence function. That is new x. And then for that new x values, we predict its y value using predict function, and its first input argument is nn.leg, right? nn.leg. And we put that new x values in it, and then predict y value. And the type is row, which means that we're gonna predict some continuous typed numbers for the predicted value. And then we plot those things. That this one is original data set, the training set, and we plot the predicted value, fitted curve using this new dot y, the predicted value for the new data set, and this new dot x is the newly generated data set. There must be many more, right? Because the increment was 0.01. And we use lines function to draw a line connecting those dots, very small increment dot, the dots having very small increment. Then you can see that this is a predicted fitted line by neural network. Okay, so neural network can be used for regression problem using the same error backpropagation algorithm. Okay, so this sentence is quite important. Neural networks smoothly interpolate the training data points. Okay, so smoothly interpolate the training data points. So you can describe the pattern of data in multidimensional space, even though this example shows just one-dimensional X example, it smoothly interpolate the data points. You can notice that. So to know, to know about more about this regression problem, about this sentence, the neural network smoothly interpolate the training data points. This slide is just shows the structure of a trained neural network. Here we have this structure of neural network with 10 weights because there are, the arcs are 10, the number of arcs are 10 is 10. And here, as I explained before, these numbers are weights. For example, this one is the weights between a bias term and the first hidden node, and then we have, because we set the number of hidden node to 3, there are 3 hidden nodes and one x1, one x input, one input, and one response, one output. So this is the structure of the neural network in this example, and using this command, you can see all those weights, and then you can make some correspondence on between these two outputs. This value is this one, and this value, the weights between input node and the first hidden node is negative 0.89, which is this one. So from this information and this information, I draw this graphical representation of the trained neural network. And this is an example of the only one x variable. So to know whether or not really the neural network smoothly interpolated the data points in a multidimensional space, this is a 2x cases. Okay, there are 2x variables. The first, here we have x1 here, x2 here, x1 here, x2 here, right? So the formula seems quite complex, but the thing that you have to notice is this fx is a function of x1 and x2. So we can visualize this function in, actually in three-dimensional space, but in this plane, in this two-dimensional space, this one is x1, x2, and this axis x1, x2, and fx. Okay, and this formula in fact looks like this one. Okay, so based on this formula, what I did is I added an error term which follows normal distribution with zero mean and with some variance, a standard deviation. So I generate based on this formula, just like what I did here. What I did is I generated the numbers on two-dimensional space, x1 and x2, and then put those x1 and x2 values in this formula, and added some random number generated from normal distribution. Okay, and this figure, this figure shows the this figure shows the generated the generated data set. So based on this data set, so this data set looks like this data set has 3 columns: x1 column, x2 column, and y column. Okay, based on that, I trained a neural network using NN function, and this is the result. So all those numbers, all those weights came from the result of the mnet function. And then now after that, I computed the R square value, and the R square is 82.16, which is quite a large number, which means that in fact the trained neural network smoothly interpolate all those the training data points. Okay, so then the fitted neural network must look like this surface. Okay, the surface interpolating the among those data points. Okay, and what I did additionally for the training neural network is, in fact, in this previous example, we have 3 columns: x1 column, x2 column, and y column. In addition to those columns, I added 3 more columns with the same number of observations. And these 3 columns, the numbers in these 3 columns were generated from uniform distribution. Okay, so we know that there is no relationship between these 3 values and output the response value, the y value. Okay, there is no any relate, because they are the uniform random numbers. These 3s are uniform random numbers, so there is no relationship between y and these 3 x variables. So based on based on this data set, having x1 column that previously generated from this model, this equation, and the x2 column that is also generated from that this equation, okay, and I added 3 more columns generated from uniform distribution, okay, and there is a y column that is also same as before. And based on this data set, I trained a neural network using that nnet function. Okay, that is the trained neural network. So this is an example of, previously this example was 3-dimensional space. We can imagine the surface at 3-dimensional space. Then in this case, we have to imagine a surface in 6-dimensional space, right? And this is the trained neural network. And if we closely take a look at the trained weight values, we can see that the weights connecting between x1 and hidden nodes and the weights connecting between x2 and the other hidden nodes, the absolute value of those are quite relatively big compared to the other weights, right? Connecting between these x variables and hidden nodes, the absolute value of w values are very relatively smaller than these values. It means that these 3 values does not affect a lot to this response, right? So this neural network has a kind of ability to screening out some unrelated independent variables, x variables, okay? And still we have we have a good number of R squared value, which is little smaller than this value, but because we added some noise here, the reduce of the R squared value is quite obvious, natural thing, trivial, but still we have a good number of R squared value. Okay, so we still can use the neural network for regression problem, and because if we this is the case of having only one y value. But if we want to predict two responses, two y values at the same time by only one training, we can still do that by placing one more output node in output layer. Okay, we can do that. 3 output, 4 outputs, that's okay. But the thing is that, as you can see from the very beginning of this slide, please notice that uh, for even this very simple structure, the equation is quite complex. So obviously, this structure has quite complex form, even though it is a closed form with respect to x variables. That equation, that formula must look very complex. Okay, please. So the interpretation is impossible. In fact, so that's why people say this neural network is a kind of a black box, because we cannot interpret the trained model. But in the case of the linear regression, we can make an interpretation by taking a look at the regression coefficients, right? But in this case, even for this simple structure, by taking a look at this formula, we cannot make any interpretation for y and axis, right? We cannot notice that. So that's everything about the neural network, and I hope you please understand the way of training a neural network, which is a error backpropagation algorithm. And in that algorithm, please notice that there is a multiplication of the partial derivatives to update the weights using gradient descent method. So again, neural network is on training a neural network is on solving is a kind of solving optimization problem. Please remember that. In Korean, 뉴럴넷이 이렇게 단순히 사실상 이 예측값과 실제값의 차이를 최소화하는 그런 목적으로 학습된다는 것을 뉴럴넷을 사용하는 굉장히 많은 사람들조차 잘 모르고 있는 경우가 많습니다. 그래서 그냥 그걸 좀 알았으면 좋겠다. 이제 이게 제 바람입니다. So, because the way, in fact, the implementation of this error backpropagation algorithm, it must be hard work. So I will never give you a problem implementing this error backpropagation algorithm. So don't worry about it. Okay, so just please understand the way of training the neural network. Thank you for your attention. I'm gonna finish here, and from the next class, we're gonna take a look at unsupervised learning case, the clustering case. Thank you for your attention.